Okay. Great. All right. Well, thank you so much, everyone, for joining me today to talk a little bit about this subject. I think it's a fascinating subject, and I hope you will agree, or I hope I can convince you. If you're not already interested in some of this stuff, maybe I will pique your interest a little bit. I regret that I can't be there with you in person. I was very much looking forward to that, but this is the world we live in. So thank you so much for joining me virtually to talk about planetary science. This is going to be a broad overview of this field. Some stuff about our solar system, some stuff about exoplanets, which is particularly of interest to me. That is my field of research, is exoplanets, as well as exomoons, really, the moons of exoplanets. That's what I mainly work on. But I've always had a fascination for our solar system and the many worlds of our solar system. And we'll also talk a little bit about the history of our understanding of planets, not just our planet, but especially the other planets in our solar system and beyond. So why don't we go ahead and get started? Let's see here. First of all, why do we care about this? This is where I always start my presentations. Why should we even care about learning about these things? Why should we study planetary science? By the way, this is a real photograph. I just love this image, just pointed out here. This is a real photograph of the Earth with the moon in the foreground. This is not a composite. I think it's just an incredible image of the far side of the moon and the Earth. And a beautiful pair it is. But why do we care about doing this work? Well, I think there are lots of answers to that question. To start with, I would say that planetary science is really a comparative science. When we study the other planets in our solar system and the planets beyond our solar system, they are, of course, very interesting in their own right. We just want to know everything that we can about nature, and these are fascinating worlds. But part of what makes them so fascinating is how different they are from our own planet. And you can see at a glance, looking at our solar system, how different all the planets are, one to the next. And, like I say, we're interested in those planets, but they're also telling us a lot about our own planet. And of course, that is very, very important. Think, for example, about the climate, right? We're very concerned about Earth's climate. Well, look at Venus and Mars. These are two planets that, compositionally kind of similar, roughly the same distance from the sun. Depending on how you define it, they could all be considered part of the habitable zone. We know that Mars once had liquid water on its surface, no longer. Venus, very, very hot. Mars, very, very cold. Both extremely desolate places. So change just a little bit. And a place like the Earth can be very, very inhospitable. So studying these planets also helps us hold a mirror up to ourselves. We're also very much interested in understanding our origins. Who are we? Where did we come from? What is the history? Long, storied history, 4.5 billion years on the Earth. What happened? All this, from the formation of the Earth up into the present. It's a fascinating history. And these are questions that are very profound and have been treated historically mainly by the major religions of the Earth. Every culture seems like has their own investigations of what the creation of the world, the creation of the universe. And it is just in the last few hundred years, I would argue, that through the study of planetary science, we're really starting to answer a lot of those questions, not through religion, but through science, and really providing some hard answers to some of these questions that have preoccupied us for a very long time. Talking about the birth of a planetary system, here's sort of an overview of how it happens. In the Milky Way galaxy, of course, where we live, there's a lot of gas and dust, a lot of raw materials around. These giant clouds, they can be several light years across. And what happens is that eventually they start to collapse gravitationally. They form these, what we call dense cores. It gets hotter, it gets more and more dense. Eventually, you collect enough material in the centers of these cores that you can create a star. High enough pressures, high enough temperatures that hydrogen fusion starts. And then you have the birth of a star. But that's not the end of the story, because you have the star sitting at the middle, and then now you have a disk of material. This material has flattened into a disk of gas and dust, and this disk is eventually what gives rise to the planets. And so we're left at the end with a nice ordered planetary system. But, and we've been seeing now in the last several years, last 10 years or so, these incredible images coming out from ALMA, from the microwave telescope array down in Chile, imaging these, what we call protoplanetary disks. And these disks of material, we're learning so much about the early years of planetary formation from these images. And I wanted to point out this one in particular. What we're looking at here is the PDS-70 system. And I don't know if you can see my mouse, but this object right here is PDS-70C. It's a planet. And what's so exciting about this is not just that we're seeing a planet embedded in this disk of material, but we can actually see another disk of material surrounding the planet. And it is believed that in this disk, the moons of this planet will eventually form. And this is the first time that we've ever been able to see something like this. So, we want to understand all stages of life from beginning to the end of planetary systems. So we have to look at a lot of different systems because we always see just one snapshot in time. But these protoplanetary disks in particular are telling us a lot about how planetary systems form. And believe it or not, there's still a lot of open questions about how this happens. We know that you can start with these very, very small particles, gas and dust, microscopic sized particles. And we know eventually we end up with asteroids and comets and rocky planets and gaseous planets. But how do you get from the microscopic to the very, very large? That's still very much an open area of research. And there are competing theories. For example, it's thought perhaps that you have these little particles, dust or ice, sort of attaching themselves to one another in a non-gravitational sense. And then eventually they get large enough that they can use gravity to accrete material and make the planets that we see. But that's maybe not how it happens. Instead, you have gas, a lot of gas and dust again, turbulence and instabilities in this gaseous disk that creates, effectively like eddies, sort of high density areas in the material. And out of that, these planets are sort of formed that way, not through gravity, but through sort of fluid dynamical overdensities in this disk. Maybe it's some combination of the two. Maybe there's some other explanations that we haven't really come up with yet. The point is really just that this is very much a question that is an active area of research, including folks at ASIAA really interested in these questions of planetary formation. And then, once you have these planets kind of formed, the general picture, this sort of emerging picture, is that where we see the planets today is not necessarily where they were born. Instead, they were formed in one place, and then they might migrate. They might migrate through the disk. It's thought that this happened in our solar system, for example. So you have the objects that eventually would become Jupiter and Saturn and Uranus and Neptune. Here in this picture, they have migrated quite a bit inward and moving around a whole bunch of material in the process. And then eventually they migrate back outward to the distances we know them today. So this is always very important to keep in mind where the static picture or what we see in a planetary system now doesn't necessarily mean that they were formed that way. It's very important to keep that in mind when we're thinking about the formation process itself. And then finally, we really want to understand not just our planet, but also our solar system in the context of the Milky Way galaxy. There are a few 100 billion stars in the Milky Way galaxy. It's thought that most of these stars will have planets. And so, how does our solar system stack up against these others? In what ways is it typical? In what ways is it not so typical? That's really very much an open question. And there's a lot of observational challenges, for example, to find planetary systems that look like our planetary system. It's not so easy. And so we have to, really think carefully about our observational biases and understanding what we're seeing out there and how does it relate. Are we common? Are we not so common? This is, I think, a very important question, especially since it relates to the search for life. And this is an endeavor that I know not every astronomer is so excited about, but for me, this is a really profound part of what we do. Looking for life. Life is really special in the universe. We know that much, but how common or how rare it might be, that's an open question. And so, here, where do we find life? We find life on the planet Earth. So, it's a good bet that if we're going to find life elsewhere, planets are a good place to look. Not just any planet, though. We've started to think about what kind of things life needs. One of the principal ingredients of life is liquid water. So we focus on this thing called the habitable zone, this region of space around a given star, not too close, not too far away from the star, but just right so that you can have a stable liquid water on the surface. Too close and it all evaporates away to space. Too far away and it is all frozen, all locked up in ice. So we want to be just the right distance. And this, believe it or not, is even also kind of controversial. Depending on how you define it, maybe Venus is in the habitable zone, maybe Mars is in the habitable zone. Obviously, just because a planet is in the habitable zone doesn't mean it is habitable, and it doesn't mean it is inhabited. It just is one sort of condition. But we're also interested in the chemical composition of these planets, right? We are made out of chemical elements and molecules. We have some sense of what life on Earth needs. Maybe life elsewhere needs the same things. Maybe life elsewhere has some different requirements and some different biochemistry. That's an open question. And so when we look at these other planets, whether they are in our solar system or whether they are in other solar systems, we're very much interested in the question of what are the raw materials that are present on this planet? Could it be a toxic environment? Could it be a very natural, nice environment for life to arise? These questions we're always thinking about when we are examining these planetary systems. So with all that out of the way, let me go through a brief history of planetary science. And I have put in here Western history of science because, frankly, that's what I'm most familiar with. It should be quite obvious to all of us at this point that astronomy is a very ancient tradition that has been shared by cultures all around the world. The planets have had a special significance to cultures all around the world. So our understanding of what the planets are has clearly been evolving over the course of thousands of years, and it has gone at different paces in different places. So I'm going to talk specifically about Western history of planetary science. So you'll bear with me on that, but just make it clear that these are not the only important figures in this history. But you may have heard that for a very, very long time, our picture of the solar system and really the universe as it was understood at the time was not quite right. We had this thing called the geocentric model, which means that the Earth, rather than the sun, sat in the middle of everything, and not just the planets, but the moon and the sun even all were going around the Earth. And this is generally, this model is associated with this fellow here named Claudius Ptolemy, a Roman mathematician and astronomer. This model held sway for a very, very long time. It was not the only model, but it was the dominating model for a very long time. Actually, it explains what we see in the night sky very, very well. You will see in this image here, they don't just travel on these circles. They also have these other circles called epicycles. And with those modifications, it actually works pretty well as a model of the sky. But of course, we now know that that is incorrect. And so we attribute our more modern understanding of what's going on up there to this gentleman here, Nicholas Copernicus, who introduced the heliocentric model. Now, he, again, is not the first. There are Greek philosophers, natural philosophers, mathematicians, Aristarchus of Samos, for example. came along 2,000 years before Copernicus, who had similar ideas. But clearly, those ideas did not catch on broadly until the work of Copernicus, who, instead of having the Earth at the center, placed the sun at the center and had all of the planets going around the sun instead. Now, this model, even though we give Copernicus a lot of credit for it, is not exactly right either. For example, Copernicus has all of the planets on circular orbits, and he has all the planets moving basically at the same speed. We know that that's not correct. So we give Copernicus a lot of credit, but that's not the entire picture. And this was published, by the way, right around the time of his death in 1543. So we need more contributions from more scientists. Very important contributions from Johannes Kepler, who took the Copernican model and modified it and produced the laws of planetary motion that we still use today. I looked them up. I should know them by memory, but I use them all the time because they are fundamental laws of planetary motion. Kepler discovered that it is not circular orbits, rather they are elliptical orbits on which planets travel. There's an ellipse, and the star, in this case, the sun, is at one focus of this ellipse. He also found that the speed of the planet changes depending on how far away you are from the planet. From the host star. If you're far away from the star, you're moving more slowly. If you're close to the star, you're moving more quickly. That's the foundation of Kepler's second law here, which says equal areas and equal times. The planet is moving slower out here and faster here. And as a result, the areas of these two essentially triangles are the same. And then Kepler's third law, very important, the period of the orbit squared is proportional to the semi-major axis cubed. This is the major axis here, the long axis of the ellipse. And so the semi-major axis is half that. And so this is the semi-major axis here. Quantity cubed is proportional to the period squared. I always think about that in terms of Jupiter, actually. Jupiter has something like a 12-year orbit, and it orbits about 5 astronomical units away from the sun. So if you do that math, it lines up pretty cleanly. So Kepler's third laws, we're still using them today, hugely important. And then moving on to Galileo. You've probably heard about all of these figures, so apologies if it's review, but these are very important contributions. Galileo is, of course, made important contributions in physics, but what we're going to talk about here are his contributions to observation with the telescope. He acquired a telescope of Dutch manufacture and turned the telescope towards the sky. He's the person we generally credit for doing this first. Maybe other people looked at the sky but didn't make the same kind of contributions he did. But several very important contributions. Sketching the moon, observing the moon through the telescope and seeing for the first time craters and mountains on the moon. And this is really kind of responsible for making the moon a real place, a planet in its own right. Of course, you look up at the moon, it's a full moon tonight, of course, you can see surface features, but until you really see it through the telescope, you can't fully appreciate how this is a place, mountains and valleys, and you could go there. Of course, going to the moon was several hundred years in the future, but these observations of the moon, very, very important. Not just the moon, but also observing the planets. These sketches right here are Galileo's sketches of the planet Venus. This is hugely important because what you can see here is that Venus is going through phases, just like the moon, and also it's changing its size. So what's happening here is that when we see Venus like this, it's on the far side of the sun, so it's very, very far away from us, or comparatively far away from us, and we are seeing it fully illuminated. And then as it approaches us, it comes around. Now it is, almost between us and the sun, so it's much, much closer. And now we are seeing it from the backside, so it's only very partly illuminated, just like the moon. And so this is an important demonstration that the Copernican theory of a sun at the center is fundamentally correct, right? you couldn't have this with a geocentric model. And then finally, Galileo's observations of the moons of Jupiter, the 4 large moons of Jupiter, I should say, which in fact still bear his name. We call them the Galilean moons. And so here are his sketches over the course of about 2 weeks. And he's got Jupiter here, and he's got the moons, just little points of light in his telescope, but they're moving around each night in a different position, again demonstrating that the Earth is not the center of everything, because in this case these objects are clearly going around Jupiter. Moving a little forward in time, we come to the discovery of Uranus, another incredible moment in our history of planetary science. Discovered by William Herschel in 1781. This is the first planet discovered with a telescope. All the planets out to Saturn you can see with your own eyes. Just look up in the sky, and if it's up there and it's a dark enough sky, you can see it. You can see all the planets out to Saturn. But Uranus is not possible to see with the naked eye. And so William Herschel was looking for comets, actually, and stumbled upon the discovery of Uranus. And it's twice as far away from the sun as the planet Saturn. So this was a huge revolution at the time, new planets to be discovered with the telescope. And so obviously it became a very attractive target. What astronomers eventually noticed as they observed Uranus moving through the sky over the course of a few decades was that Uranus wasn't really behaving the way it should be. It wasn't moving like the other planets. Something was wrong. It's going too fast or too slow. Something's not right. So what's wrong here? Is there a problem with Kepler's laws? Well, turns out that that's not the problem. The problem was that there's another planet beyond the orbit of Uranus that is affecting Uranus's orbit. So it was computed, it was predicted that another planet is out there. And so these 2 gentlemen, Urbain Le Verrier and John Couch Adams in France and England, respectively, set about trying to calculate the position of Neptune. They were both working on it at the same time. It's an amazing sort of coincidence that these 2 people were working on this problem almost, right at the same time. Le Verrier produced a calculation and said Neptune should be right there. And he handed it to an astronomer friend, and the astronomer found it that very night. So this is another incredible discovery in planetary science, because this is the first time that a planet has been mathematically predicted. We can use mathematics to predict where a planet is going to be, and we can point our telescope and it's right there. And I don't have any slides about Planet 9. Maybe you've heard about Planet 9, but Planet 9 is a hypothetical planet that has been predicted to exist very, very far out in the outer solar system. And the scientists working on that, again, have been using mathematics to try to understand where this object might be in the sky, if it's really there. And now, of course, mathematics is a huge part of the work that we do as astronomers. And prediction, of course, is very important in science. Actually, when we were looking for Neptune, or after Neptune was discovered, again, it was thought that there was some problems with Neptune's orbit. And so yet another planet was predicted to exist beyond the orbit of Neptune. Now, it turns out that there actually wasn't any problem with Neptune. Our numbers weren't good enough. Our observations weren't good enough. So turns out there wasn't really a discrepancy with Neptune's orbit, but it was thought at the time that there was. And so this renewed the search for objects in the outer solar system. And that led to the discovery of Pluto, which we now call a dwarf planet, because we now know it is one of many tens of thousands of objects out in what we call the Kuiper belt, sort of a second asteroid belt beyond Neptune. And so this object was discovered, kind of what we might call the lowest hanging fruit, the easiest one to see of this very, very distant population of objects. And it was discovered by Clyde Tombaugh in 1930, just taking photographs over the course of subsequent nights, blinking them back and forth and looking for something that's moved. This is incredibly painstaking work. And so it is a remarkable discovery of its own. But moving forward about 30 years, all of a sudden we enter the space age. Now we can visit these planets close up for the very first time. And this is just absolutely revolutionary in terms of what we can understand about these planets. Now we don't have to just see them through the telescope. We can go visit them, see them, orbit them, fly by them, land on them in some cases. So this is just a truly remarkable period, and we're so fortunate to live through it, frankly. This is a diagram of the missions that have been flown to the various planets in the Earth. I think this is quite nice. I like these diagrams so much that I include two of them here. I think this one really makes clear how many missions there have been. This is the Earth here. So Venus has got a lot. This is the moon. So many, many missions to the moon. Mars here, and fewer missions as we go to the outer solar system. So we've really been quite busy. It's very exciting time to be alive, frankly. Of course, you're familiar with the human landings on the moon. 6 landings of human beings on the moon, 12 astronauts between 1969 and 1972. They collected hundreds of kilograms of moon rocks and brought them back to the Earth, of course, and we're still studying them today. So many interesting geological studies to be done on our nearest neighbor. And you probably know that we're going back. NASA has plans to return to the moon with Artemis. Artemis is the sister of Apollo, appropriately enough. This time the astronauts are intending to land on the south pole of the moon, where it's thought that there is a great deal of ice, water ice deposited in the permanent shadows of the South Pole. So that's where they're going. There was talk of having this happen as soon as 2024. I don't think that's going to happen, but certainly I think within the end of the decade, by 2030, I think it's a safe bet that we should see human beings on the moon once again if everything goes to plan. So that's very exciting. Talk about our other nearest neighbors. This is Venus, of course, is our nearest neighbor. Venus is covered in clouds. This is what we're seeing on the right. You can't see the surface, at least optically, but we can use our sophisticated tools. This is a radar map of Venus. Obviously, it's a false color. They've just used different colors to accentuate the different compositions of the rocks here. Very, very interesting place, but you probably know it is inhospitable. So we've had flybys and orbits. It's not really easy to land on Venus, but we have in fact done it. The Soviet Union in particular, between 1966 and 1984, sent a lot of landers. I don't even know how many, but they sent a lot of spacecraft to land on the surface of Venus. Many of them failed, but a few of them were successful. They land on the surface of Venus, so inhospitable, 450 degrees Celsius, and atmospheric pressure of 93 times the atmospheric pressure here on the Earth. That's equivalent of being 1 kilometer underwater in Earth's oceans. Absolutely crazy, the environment on Venus. So these spacecraft, they land, they have enough time to take a few pictures, take a few readings, and then they're fried and melted and crushed by this inhospitable environment. So, don't expect to see people walking around Venus in our lifetime. It's really just kind of too hellish of a place, quite frankly. But look at these images. They are just amazing. What an alien environment it is. But all hope is not lost for Venus. It's actually, this is super cool, I think. There is an altitude on Venus where the atmospheric pressure and the temperature is kind of like what we have here on the Earth. Now, there's not a lot of oxygen the way that we have here on the Earth. It's mostly a carbon dioxide environment. But there is an altitude where you could place an airship and then you could operate at, very comfortable temperatures and pressures. This is obviously an artistic rendering, and I think this is many, many years in the future. And by the way, these airships are not filled with hydrogen or helium. They're in fact vacuums. That's as buoyant as you possibly can get. Fill the airship with nothing, and it's got a lot of buoyancy as a result. So these are real plans, not exactly these artistic renderings, but there are real conversations happening now about how we might one day have atmospheric missions in Venus. So that's extremely exciting. You, of course, have seen these incredible images from Mars. We've been in the Mars game for a very long time. Landed on Mars first in 1976 with the Viking lander. And then we had a series of rovers that have been exploring the surface. And these have all been so amazing, so successful, these missions. When they first started these rovers, they'd say, well, we want it to last for 3 months. And then it would end up lasting for 5 or 6 years or something like that. They really over-engineer these missions. And so these rovers have been driving all around the surface of Mars, probing the soil, looking for water, looking for signs of life. And of course, we are still literally just scratching the surface. But you probably know that there are long-term plans to return, to send human beings to the surface of Mars. That's a very, very challenging prospect, but there's a lot of interest in it. So I think, if we take care of ourselves, we might live to see it, or I might live to see it. I expect you probably definitely will. So that's super exciting. Mercury, finish off the inner solar system with Mercury, the innermost planet of our solar system. Looks a lot like the moon from the outside. This is, of course, a false color image as well, to once again accentuate the surface material of this planet. It's actually very, very dense. It has a huge core compared to how large the planet is. So it's kind of an open question. I'm not sure how whether we've solved that issue, but it's a very interesting planet and very difficult to get to, actually. You kind of think, well, all you have to do is just kind of fly in the direction of the sun. But the problem is that you'll pick up way too much speed if you just fly directly there. You'd be traveling so fast that you'd never be able to slow yourself down and go into orbit around Mercury. And so what this spacecraft did, the Messenger mission, actually had like 10 or 11 gravitational assists. Flew by Earth and flew by Venus and flew by Earth again and flew by Venus again to just gradually slow itself down so that it could arrive at Mercury and not be going too fast when it got there. So that was really an incredible mission, 2011 to 2015. Now pushing into the outer solar system, we have visited Jupiter a number of times with the Pioneer 10 and 11 spacecraft, with Voyager 1, Voyager 2. Actually, New Horizons flew by Jupiter, Galileo mission to Jupiter, and now we have Juno. And Juno, you may have seen, has been returning these incredible images of, close-up images, the closest up ever images of Jupiter. And you can just see the incredible, richness of what's going on in the Jupiter atmosphere. You look at this image right here, you can see for the first time three-dimensional structure in these clouds. And so this is, really providing, this is not my area of expertise, of course, but, to understand Jupiter at this kind of detail is really remarkable. And this is actually Juno's orbit here. You may be aware that Jupiter has very, very extreme environment in its vicinity, these high radiation belts where charged particles are extremely energetic. And if you spend way too much time in there, it's going to fry your spacecraft. So in order to get close enough to Jupiter that we can obtain these images, what they have to do instead is put it on this very elliptical orbit. So it spends a little bit of time flying near Jupiter, and then it spends most of its time well outside of these radiation belts. So Juno has been incredible. They've released these very high resolution images, which you can print out and put on your wall. I have definitely done that myself. Here's a close-up look of those Galilean moons, the 4 moons that Galileo discovered all the way back in 1610. Now we can see them close up. This is Io, the innermost moon of Jupiter, covered in volcanoes spewing out sulfur. Europa, Ganymede, and Callisto, these are icy worlds. Europa in particular is a very exciting place. We've long thought It's one of the most attractive astrobiological targets, covered in ice, but underneath that ice is a global liquid ocean. And so we've been, if we're looking for liquid water, this is a great place to look. And so we are sending a dedicated mission to Europa in the next few years, launching in 2024, scheduled to arrive around 2030. And its entire mission is to study Europa, close up, understand what's going on there. Won't land, unfortunately, but hopefully there's a lot that we can do from orbit. By the way, it's spewing material out into space. And so there's a chance that you can even, study that material and understand what's going on beneath the surface. Basically, this is water. It's coming from underneath the ice, spewing out into space, and you can observe that close up. Moving out to Saturn, we have the Cassini-Huygens mission. This is another amazing mission. It spent 13 years in orbit around Saturn and returned literally tens of thousands of the most breathtaking images from the Saturn system. This is Saturn, of course, with the rings, and Saturn's largest moon, Titan. We'll talk more about that in a second. Just so many incredible images of Saturn, its rings, its small moons, its large moons. Here's a sample of some of its moons. Iapetus, Titan, Mimas, Dione, Enceladus, Hyperion, and Pan. These are not to scale, by the way. Titan is by far the largest. This is Hyperion here, much, much smaller. But look at the surface detail of this thing. And look at this guy, this Pan, this little moon right here, maybe only 10 kilometers across or so, with this equatorial ridge. It looks a little bit like a ravioli or something, like a dumpling. There's just so much diversity in these moons, and they each tell a unique and special story about this planetary system and our solar system as a whole. Enceladus, another one of these very important moons, like Europa, is also thought to have a global liquid ocean underneath this icy surface, and once again has geysers of material spewing out into space. We've seen these specifically at the South Pole. So this is some imaging of these geysers spewing off of the surface. And here's a little diagram of what we think is going on here. So these moons are gravitationally squeezed by their host planet. That injects a lot of energy into these moons. And so as a result, you can have these geysers, and maybe you have something like hydrothermal vents. Hydrothermal vents being, these places where hot water and chemicals are spewing out of the earth underneath the ocean. And on Earth anyway, these are kind of like oases, meaning places where life really thrives in the middle of this barren ocean floor. Where you find the hydrothermal vents is where you find life is just thriving at these points. And so again, could there be life in the oceans of Enceladus? Very much an open question. Going to be a long time before we can get an answer to that question, but it's a hugely exciting prospect. I mentioned Titan before. We have actually landed on Titan. This is some images from the Huygens probe. I mentioned Cassini-Huygens. Cassini was the orbiter, spent all this time orbiting Saturn. Huygens actually landed on Titan. This is an image here taken from about 5 kilometers above the surface. And then this image, this precious image here, is taken from the surface of Titan. Just these tantalizing little glimpses of what might be happening on Titan. But the good news is that we're going back to Titan with a mission called Dragonfly in 2027 to arrive around 2034. And this is a drone. It's going to fly around. So I can't wait to see this. This is going to be revolutionary in terms of what we understand about Titan. Titan, by the way, the only moon in our solar system, the only place outside of the Earth that has a thick atmosphere. This atmosphere contains a lot of hydrocarbons, methane and ethane. And believe it or not, there is stable liquid methane on the surface of Titan, the only place in the solar system where you can have stable surface liquid. It's not water, of course, it's methane, but a very, very interesting, intriguing, unusual place. And so we are going to start exploring it in about 12 years or so with this drone. I can't wait. Going out even farther into the solar system, Uranus and Neptune. These two fascinating worlds have been visited only a single time by the Voyager 2 spacecraft. Flew by Uranus in 1986 and flew by Neptune in 1989. So every close-up image you have ever seen of these two planets came from that one mission. I think it's long past time that we go back and visit these planets again. They have a whole bunch of interesting moons as well, just like Jupiter and Saturn. And our recent studies in the field of exoplanets have revealed that this class of world, intermediate in mass between Earth mass, these what we call rocky or terrestrial planets, and the gas giants like Jupiter and Saturn. These planets are sort of halfway in between, and this class of planet is evidently the most common type of planet in the galaxy. So we're really interested in knowing more about these planets. Unfortunately, they are so far away from us that it is hard to get there and hard to study. But there are plans in the recently released decadal survey, Planetary Science. It set as a primary objective for the next 20 years or so to push forward with an orbiter mission to Uranus. So we are going back. We're going to have to wait a long time to get there. But one of these days we will go back to these planets. And we have every reason to expect that there's going to be so much to learn as a result of going there. We have gone even farther, though. I mentioned New Horizons before. New Horizons flew by Pluto and Charon. These are, again, false color images to highlight the surface differences. Here's Pluto. This is Charon. These are they are not that close to one another, but this is about their relative size. Charon is a very massive moon compared to Pluto. On the surface of Pluto, we've seen nitrogen icebergs moving around, evidence of recent surface activity. These icebergs floating around on the surface. So it's a fascinating place. And as I said before, one member of this sort of second asteroid belt called the Kuiper Belt, kind of like an icy asteroid belt out beyond Neptune. And New Horizons, traveling so fast, it can't go into orbit. It just flies by. So all the images we got, were taken over the course of a couple of days as it flew by Pluto and this Pluto system. Fortunately, they extended that mission, so it is now observed a second object and is going on to observe yet another. This object here, called Arrokoth, has this long phone number here. Arrokoth, very, very far out there, obviously beyond Pluto. And I've set it next to this object, Comet 67P, also called Churyumov-Gerasimenko. Comets, you may know, are icy objects that come to us from the outer solar system. So why should I put these two together? Well, you may notice some similarities here. They both have this sort of two-lobed structure here. And these are sort of the building blocks of the solar system. And so this provides some important insights. We can understand by looking specifically at these smaller bodies, kind of fill in that picture that I was talking about before. How do you get from the small objects to the very large objects? Well, these objects kind of sit right in the middle. And so what's happening there? Well, the thinking is that these things are sort of coming together. They're icy. They might stick together. These bigger objects, they're sort of orbiting each other very, very slowly because they're low mass. Eventually, they collide, but very, very gently, and they fuse together into this sort of two-lobed structure. So you see it in both of these. And also we now know that a lot of these Kuiper Belt objects, even very, very small objects, they basically all have moons, believe it or not. So, the picture is continuing to emerge, how these objects form, go from the small to the large. So many insights by studying these objects. And now, finally, at long last, we move on to the era of exoplanets, studying planets beyond our solar system. It's such an exciting time that we're able to do this. The planets in our solar system, there's still so much to understand about those. They will occupy us for centuries to come, so long as we are still in the space exploration game in centuries. I sure hope we are. But the exoplanets in the meantime are revealing all kinds of amazing new things. So you might wonder, how do we find these planets? You may have heard a little bit about it. Obviously, we're going to use telescopes. But then what do we do with them? Well, I actually, believe it or not, had a student one time who thought that this image we're looking at here was a photograph of an exoplanet. She said, look, this particular exoplanet has great oceans and clouds and mountains. And she thought this was a photograph. And no offense to her, this is a very photorealistic planet. It really looks real. But unfortunately, this is not the kind of image that we get. Instead, if we want to directly image exoplanets, this is about the state of the art. This is about as best as we can do. And this is actually a really cool video. This is a few years old, as you can see, but this is the planet Beta Pictoris. We're seeing it orbit this star here, more or less edge on. It's quite a good distance away from its host star. And what we're seeing here is not actually reflected light. This particular system is very, very young. And so we're seeing actually the heat left over from its formation. This planet is still sort of shining by its own light in the infrared. And that's how we're able to see it. This big black disk here is a result of the fact that the star is, 100,000 times brighter than the planet. So the only way that we can hope to see the planet is if we block out the light from the star first. And so that's what we have to do here. Very, very complicated observations. So you can imagine, what are our requirements for doing something like this? We need the planet usually to be young, so it's still shining this way, because the light it is receiving from its star is way, way too weak for us to detect. And also, we want this system to be fairly nearby to us. You can imagine that if you have a star and a planet, the farther away that you put them, the closer they look together in the sky. So we want them to be close up so that we have some big distance here. And clearly, we just can't see planets that are orbiting super close to the star because that is, it's so bright in that region. We have to block it off. We just wouldn't see planets in that region. Here's another absolutely incredible animation, this time of the HR 8799 system. We're seeing here 4 planets, 1, 2, 3, 4 planets in orbit around the star. This time we're seeing it face on. We're kind of looking down on this planetary system. And look at this size scale here, 20 astronomical units. This is the distance from the Earth to Uranus. And so these planets are very, very far out from their host planet. And so, you probably remember that planets, the farther away they are from the sun, or their host star rather, the slower they move. And so it's really amazing that we're able to see these planets moving. You look at the time scale here. This is a 6-year movie. Observations started in 2010 and go all the way to 2016. So this is just another amazing movie. And these are the kinds of things that we can do with direct imaging. But unfortunately, as I said, direct imaging is not appropriate for every planetary system. The good news is that we have other techniques. So what are they? Oh, one more thing to say about direct imaging. These are simulations about what we might see in the future with one leading candidate for the next generation space telescope after JWST. This is called LUVOIR. And it's thought that, depending on how they build it, we might be able to see systems that look kind of like our solar system. This is our solar system seen from outside with something like LUVOIR and a star shade. I won't go into that, but that's very challenging from an engineering perspective. But one day we might really be able to produce these sorts of images, which would be absolutely amazing. So instead, we use other methods. You may have heard of the radial velocity method. This is measuring, the movement of the host star. Of course, the star is pulling on the planet gravitationally, but the planet is also pulling on the star gravitationally, and we can measure that. This is an artistic rendering of 51 Pegasi B. This planet, and this is the data on that planet, discovered by Mayor and Queloz in 1995, and this is the work that they won the Nobel Prize in Physics for a few years ago. And here's how it works. So as I said, the planet is orbiting the star. Star is pulling on the planet. Planet is also pulling on the star, and so the star is tracing out an ellipse. And so that means, from our point of view, sometimes the star is moving towards us, and other times the star is moving away from us. And so when the star is moving towards us, the light gets pushed in a bluer direction, kind of gets squeezed and looks bluer as a result. And as the star goes away from us, the light waves get stretched out and it appears red to us. And so we say that this is red shifted and blue shifted light. Here's a sort of an animation of what's going on here. Again, you can see that the planet and the star are really kind of orbiting one another. This is the center of mass here. And so if we are an outside observer, we can see the star coming towards us and coming away from us, oscillating back and forth like that. And then here, down here on the bottom, is our spectrum of light that we're receiving from the star. The dashed lines are our sort of laboratory reference. And then we see these absorption lines moving to the blue end and moving to the red end. And depending on how shifted they are in one direction or another, will determine how fast they are, how fast the star is moving. And as a result, we can measure, we can measure the orbital period, because that's the period of this oscillation. We can actually measure the eccentricity of the planet, how elliptical its orbit is. And that's because if it's elliptical, sometimes the planet and the star both are moving faster, and sometimes they're moving slower. And so this oscillating signal will look a little bit different. And then we can also measure what they typically call M sin I, meaning the mass times the sine of the planet's inclination. Unfortunately, with this particular method, you can't really pull those two apart. If we're looking at a system face on like this, there will be no radial velocity of the star because it's not coming towards us or away from us. It's just kind of moving around in the plane of the sky. And if you see it like this, you're definitely seeing it coming towards you and away from you. And so you can measure a radial velocity here, but the amplitude is going to depend both on the mass of the planet as well as how inclined this orbit is from our point of view. And then really the most successful method by far has been to look for these, what happened there? Look for these things called, let's see, I just, sorry about that. Look for these things called transits. This is when we're observing the star and the planet passes in front of the star from our point of view. This is a transit of Venus, which is an extremely rare event. But we've seen lots of transits in other planetary systems. The planet passes in front of the star, backs up, blocks out something like 1% or 1/10 of 1% or 100th of 1% of the starlight. Very little amount of light that's being blocked out, but we can measure it, and we have. This has been hugely successful. So this is what it looks like. So the planet's coming in, we're measuring the brightness of the star over time, and then as the planet is in front of the star, we have this dip in the intensity of the starlight, this very specific kind of trapezoid shape here as the planet is in transit. And then as the planet leaves, the starlight returns to what it was doing before. And this is actually the first transiting planet that was ever observed. Observed from the ground, you can see how noisy it was. Just a telescope in a parking lot, basically, from David Charbonneau. He's now at Harvard, doing very well for himself. This is the first transiting planet ever. But we're doing a lot better than that. You may have seen the news from JWST, James Webb Space Telescope. Just in the last couple of days, they released this light curve, call it a light curve, of the planet WASP 96b transiting in front of its planet. And you can just see how beautiful, how clean this is. This is real data, of course, and there's some little noise, but not much. It's an absolutely beautiful light curve. And so James Webb Space Telescope is really going to be a game changer for this kind of work. What can we determine from these transits? Well, again, we can measure the orbital period. We can also measure the planet radius. You can see that the amount of starlight that's getting blocked out is going to depend on how large the planet is. So we can measure that from how deep this transit is. We can say something maybe about the inclination that we are seeing. You can imagine if the planet passes across the equator of the star, it's got a longer distance to travel than if it passes way down here at the South Pole. Much less distance to cover, and so the transit duration will be shorter. If you have a planet that's very close to the star, we'll see kind of like what we see with Venus, which is over here, it's not being illuminated at all, but over here, it's getting, we're seeing the reflected starlight on the surface of the planet. And then as the planet goes behind the star, then there's what we call a secondary eclipse. And if you're able to see this, and believe it or not, it has really been seen with some planets close to their host star, then you can measure what's called the albedo, or the reflectivity of this planet. And then one thing that's super exciting is that we can study the atmospheric composition of these planets through transits. And we have discovered at this point over 5,000 exoplanets. You can see the count up here. Transits far and away the most successful, with over 3,800 exoplanets attributed to that. You can see right here this big clump of exoplanet discoveries. We found them all over the sky, but we've especially found them right here. This is the Kepler field of view. Kepler spacecraft spent 4.5 years staring at this one patch of sky and discovered something like 2,000 exoplanets in that effort. Kepler is unfortunately no longer with us, but its successor is called TESS, the Transiting Exoplanet Survey Satellite. And this is an amazing mission. It, unlike Kepler, which just stared at that one piece of sky, TESS is looking at basically the entire sky. If you think about it for a second, you'll realize that there's some trade-off there. The more sky you look at, the less amount of time that you can spend looking at any particular part of the sky. So a good fraction of the sky, we only observe it for 27 days, and then it moves on and observes this section, and then it moves. And it does this section and this section. Every 27 days, it observes a new section. But right up here at the top, we get a full 351 days of observation. So TESS is really an amazing mission. We're going to get a lot of new planets out of this. Here's some quick demographics of the planets that we've discovered. This is mass on the y-axis and orbital period on the x-axis. Our Earth, by the way, is right around here. So you can see that the planets that we have discovered so far are really not very Earth-like at all. Instead, what you can see here are those observational biases that I was mentioning before. It's a lot easier to see planets on short orbital periods than it is to see planets on long orbital periods. And it's also easier to see bigger planets or more massive planets than it is to see lower mass planets. So we've got a huge range here, almost, 20, 30, 40, 50 Jupiter masses. These are really kind of not even proper planets anymore. We might call them brown dwarfs. The brown dwarf limit is right around here, actually. Everything above this line is really, we might call them brown dwarfs. But a huge range in masses, down to Earth mass, and a huge range of periods, less than a day in some of these cases, and all the way out to 1 million or 10 million or 100 million days. These are these stars out here, and these are the planets that have been imaged directly, direct imaging. As I said before, you need these planets and these stars to be very separated from one another. And so direct imaging is particularly good at seeing massive planets that are very far away from their host star. And here's a histogram of our discoveries year by year. That starts in 1989. Really, there's not much out there. Arguably, the first planet discovery is in 1992. But things really get going right around here. And this is when the Kepler mission starts. And you can see transits just running away with it. And as I said, now we have about 5,000 100,000 exoplanets cataloged. Here's just a little video. I won't spend too long on this, but this sort of highlights the observational bias that we're talking about here. Here in the dashed lines is the architecture of our solar system: Mercury, Venus, Earth, Mars, Jupiter, and Saturn out here. And this video is now several years old, but it shows you all the planetary systems that were known at the time that this video was made. And what you'll notice is that they're all very, very compact, right? They're much more tightly packed than our solar system. So does that mean that our solar system is weird, unusual, and that it's so much bigger than these other planetary systems? I think probably that's not the answer. I think the answer is that it is very difficult to see a planetary system like our own. And therefore, the ones that we see are the ones that are, much smaller, much more compact. And so those are the ones that we're going to preferentially see. But I'm almost out of time here. I've just hit the hour mark, so we're just about done. Bear with me. Really, the exciting new thing in exoplanets is this thing called transmission spectroscopy. What's going on here? This is the artistic rendering, of course, of James Webb Space Telescope. What happens is that if a planet has an atmosphere, that atmosphere is composed of different molecules, different chemicals, and those molecules absorb light at specific frequencies. And so if you are looking at the light of the star as the planet passes, and you look at many different wavelengths over time, what you will see is that more light is blocked out at some wavelengths than at others. We're looking here 1.8, 2.1, 2.3 microns. And you can see that the transit depths are different for all of these because the planet effectively looks larger or smaller. There's more absorption at some wavelengths than at others. And so we've been doing this with Hubble, especially. We see clouds and hazes, but then we can also see water. And out here, these are a bunch of titanium oxide lines. Of course, we know what these absorption lines are in the laboratory. We have these chemicals. We know how they absorb. Same laws of physics. And so we can map these sort of features on these spectra from the planets themselves. This is not the star's spectrum. This is the spectrum from the planet. And again, just in the last few days, they've released a spectrum from this planet WASP 96b. Frankly, a lot of astronomers were complaining about this blue line. Didn't look like a particularly good fit. But everyone was very excited about this data. JWST is really going to be a game changer in terms of what we can measure in these planetary atmospheres. And this really seems like where we're going. Again, interested in the chemistry of these planets. What is, could these planets be hospitable for life? Well, not in the case of these, what we call hot Jupiters, these planets very close to their star. But, we're developing the tools right now so that eventually we can really start to understand the composition of atmospheres, some on planets kind of like the Earth. So it's a very exciting time. So that's the end of my talk. Thank you so much for your attention. I hope you've gotten something out of it. I know we're out of time, so if you have to go, please feel free to go. But I'm happy to answer any questions you might have at this point. I'll stick around for a little bit. Thank you very much. I see a raised hand. Yes.
Can you hear me?
Yes, I can.
Okay, so could you go back to the WASP image, like the spectroscopy from the JWST, this one?
Yes.
I wanted to ask, how do you determine that those particular wavelengths are water? Because they seem quite spaced apart from what I can see on this picture.
Sure, yes. So I'll preface it by saying that this is, again, not my area of expertise. Mm-hmm. But it's a good question. So as I mentioned before, all of these materials we can measure in the lab. And actually, you can do even better than that, kind of quantum calculations. So believe it or not, these teams that are interested in atmospheric characterization, they have publish these models that have something like, like 1 million lines, all these kind of different absorption lines, these huge models that are, way outrunning the spectral resolution that we are able to achieve, right? I mean, you can imagine you have millions of absorption lines. There's no way that you can see millions of absorption lines in data that is this coarsely sampled. Even though it's brilliant data, we're nowhere near that. But the chemistry is very complicated, right? So they run all these calculations, and when they model them, they generate a model that's just going to be kind of the total of all of these lines. So if you say, for example, there's a certain amount of water in this atmosphere, well, that water should be expected to have emission lines over here and over here and over here and over here, right? So that one molecule is going to have a variety of, I call them emission lines. They're absorption lines. Yeah. So you run that chemical model, and that chemical model is going to spit out some answer. And then you model it iteratively. This is what I'm guessing here. Pretty sure this is how they do it. Run a bunch of iterative models until they find the best fit to the data. And once again, I was watching this on Twitter. A lot of people were saying, where did that fit come from?
Exactly, because
it looks a little weird. Yeah, it's a little. They will still. What they won't do is generate a model that has a bunch of spikiness necessarily. Let's see. The model should always have basically the same resolution as the data. Yes. And so, all of these sort of spiky lines have been sort of washed out anyway. But this is, clearly there's some stuff going on here that the model is kind of missing. So I don't know why they published this, but the data looks great. The model, maybe not so much, but I want to not be too shady because this is not my field.
Yeah, I was just curious because I don't actually see any absorption lines or any observable signals when I'm looking at this model. So I was wondering if you...
So I'll just point out the y-axis here, the amount of light blocked, right? So even though these are absorptions, the peaks are really the signal. Yeah. So you're not looking for troughs in this case. This is bigger peak is more light that's blocked. So more absorption at those. Yeah,
that makes sense. Thank you.
Yeah, sure. Great question. Yes, SK.
Yeah, so I'm wondering, do you happen to have a slide of the star shade you showed?
A slide of which?
A star shade, a mission in the future, right?
I'm afraid I don't. SK is referring to these two images. So I'll just explain it for the people who are in the audience, and you can go look at it later. LUVOIR, as I said, is the sort of the next generation telescope, and there's two models here. One, it says with a coronagraph, and the other with a star shade. So a coronagraph is an instrument, a piece of equipment on board the telescope itself that blocks out the light from the star and allows us to, see these planets. As I said before, we've got to block out the light. A star shade is something that is far more challenging, but really exciting. And that is that instead of having the coronagraph right on the telescope, you actually fly. Now, this is a space telescope, remember? You fly this thing that looks like a big, sunflower, maybe 1,000 miles, maybe farther away from the telescope itself. And you have to have them perfectly aligned. And this basically, blocks out the light of the star. And it is, if you can get this to work, you can really get some incredible images. But as you can imagine, two objects flying in space, independent of one another, and trying to line things up like that, that's a huge engineering challenge. They're able to achieve some remarkable stuff. But that sounds really hard. So and probably a lot more expensive too. So we'll see what we ultimately get. But a lot of people are very excited about the star shade idea because you can get some incredible images.
Thank you.
Yeah, I think I heard another hand go up, but I didn't see who it was. Or maybe somebody was leaving. Did somebody else have a question? Okay, I guess we'll call it there. If nobody else has any questions, I'm on Slack, obviously. So if you have any more questions, feel free to ask them on the Slack, and I will be happy to chat with you. And you know, if you come back into ASIAA, whenever that happens, maybe next week, I don't know. I'm not in the office every day, but let me know if you'd like to chat more about planetary science. I'm always happy to talk about it. So thank you again for joining me. I hope you got something out of it, and I hope to see some of you around the office again at some point. Thank you.